Hello students, good morning. So today, students will start with a new topic, what is the meaning of electron affinity. Okay. Last time we discussed ionization potential, today we'll discuss electron affinity, right? Now, what is electron affinity? See, affinity means what? In English, affinity means you like something, right? Okay. So electron affinity means an atom, okay, how much affinity it has got for the electron. Fine? So it indicates, that the atom has got how much like for the electron, how much affinity for the electron. Okay. Now, how will you measure that? Just, suppose you take an atom, right? You add an electron. Suppose I take A, you add an electron, right? It will become A minus. Fine. Now, when you add an electron, some energy will be involved. Clear? Some energy will be involved. Okay. Now, that energy can either come out, this energy can be released, right? Or it can be absorbed also. Okay? So two things can happen, right? Energy can be released, absorbed. If energy is released to it is called exothermic. What is it called? Exothermic. And if energy is absorbed, it is called endothermic. Now, very important is you should know like when energy is released and when energy is absorbed. That's important. Okay. Now, energy will be released whenever the atom likes to have an electron. Suppose the atom has got affinity for the electron, right? It likes to have, there'll be some reason, we'll see that later. Suppose it likes to have, then energy will be released. Okay? Like I'll give you an example now, student. Like, for example, fluorine is there. Chlorine will become F minus, right? Now here if you see the configuration of chlorine, we write 2 7. What do we write fluorine? 2 7. Now if fluorine, if it accepts the electron, students, it will become 2 8. Now you tell me 2 8 is more stable or 2 7 is 2 8 is more stable. Very good, octet, right? 2 8 is more stable. Okay, so fluorine will accept one electron because it likes to have octet, like clear. So in this case, energy will be released. So please remember, in this case, energy will be released. Okay, but suppose I take sodium. Sodium will never like to have electron. This is not possible. Tell me why, student? Sodium is what? 281. Okay. In fact, students, what will sodium do is sodium will try to lose the electron. Doesn't want like to have, right? So you have to force the electron into sodium. Sodium doesn't want. Sodium doesn't want, right? You have to force it. So in that case, you have to supply energy. Okay. So in this case, it will be endothermic. So students, have you understood like when energy will come out? Whenever the atom has got affinity for electron, it likes to have, like the energy released. It becomes more stable, right? Okay. Fine. And when it will be, when you have to force it. Sodium doesn't like to have, right? But you are forcing it. So in that case, you have to supply energy. That case, it will be endothermic. Okay? Endothermic. And some energy will be involved. Okay? Now, this energy, very important, huh? The energy that is involved, students, is also called, there is another name for this, it is called electron gain enthalpy. What is it called? Electron gain enthalpy. Enthalpy means, students, heat. So whatever energy is involved, right? Yes. That's called electron gain enthalpy. Okay? The heat that is involved. Fine? So this is what is called electron affinity. So let me recollect you now once more. An atom, if it likes to have electron, right, it will become A to A minus. Energy will be either released or absorbed. When it will be released? When the octet is complete. Fluorine likes to have, right? When energy will be absorbed, you are forcing it, right? Sodium doesn't like to have electron. Okay, Shwan? And what is the other name for this energy that comes out or released or absorbed? It's called electron gain enthalpy. Enthalpy means one's heat. Electron gain enthalpy. Fine? Okay. Fine, students. Now, let's see how this goes across the period and group. Okay, let's come to this now. So very easy now. Suppose I take helium, sorry, not helium, right? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay. Obviously, students, fluorine will like to have electron. Fluorine likes to have. Why? Because from 2,7 it becomes 2,8. Okay. So across the period, the electron affinity will increase. So please remember very, very important thing. The electron affinity increases. Okay. Across the period. But if you see down the group, like for example, if you see fluorine, generally you take any element you take, lithium, sodium, potassium, rubidium, cesium, right? Down the group, it will decrease. Okay. So very important, like across the period, if you go across, it will increase. Fluorine is the most, highly having affinity for electron, right? Down the group decrease. Okay. Swan's getting it? Fine. But Swan's here also, you have some exceptions. Just give me 1 minute. Okay, Swans, we'll continue now. So students, here also you have, let's start now. Here also you will have some exceptions. Okay. So what is the general trend? Across the period, increases, down the group, decreases, right? Okay. Students, one more very important thing, just A plus electron having A minus, right? This is called electron affinity. Okay. Or electron gain enthalpy. Now what is the reverse called? Suppose I write the reverse thing. Can I say the reverse is the ionization potential of A minus? See the reverse? Ionization, but A minus is losing electron. Can you see? Losing electron is called ionization. Okay? So I can say electron affinity of A, I can write like this. Or better I write electron gain enthalpy of A. This is a very important thing, they ask in competitive exams. Electron gain enthalpy of A is equal to ionization energy of A minus. Am I right? Ionization energy of A minus. See, A minus losing electron, right? Clear? Let me give you some examples. For example, F plus electron gives F minus, right? This is electron affinity of A, F minus losing one electron, right, and becoming F. ionization energy of F minus. Okay. So what I want to say is that the reverse is nothing but ionization potential of this. Okay. Fine. A minus. So note down this very important point. It's a very important point. Note it down. Again, the wordings are not that clear, so I will write on the top here. So what I want to say is, I'll write again the same thing, students, because I think you are not able to see down. Electron and gain enthalpy of A is equal to ionization energy of A minus. Okay. Fine. So just note it down. Okay, fine, student. Now let us see the exceptions now. Where all exceptions will come. So I told you now, across the period it increases. Okay. And down the group. Now down the group, let us take some examples. Let us take fluorine, chlorine, bromine, iodine. So listen to this very carefully, it's very, very important point. If you see these elements, fluorine, chlorine, bromine, right? Actually speaking, fluorine should have the highest electron affinity. Right? Fluorine should have the highest value. Okay? And it should decrease. Fine? Fluorine is the okay? But there is a small problem here. Instead of fluorine, chlorine has the highest. So the order is chlorine greater than fluorine, correct? Greater than bromine, greater than iodine. So why this problem? You know, chlorine, why is it got more than fluorine? Small change is there, right? Reason, students, is because of the small size of fluorine atom. See what happens, you know, fluorine is having 9 electrons, right? And the size is extremely small, very, very small size, you see. 9 electrons are there. Okay. Yes, if you add one electron, it will complete its octet. Good. But problem is, because of small size, if you are adding one extra electron, there will be lot of repulsion. Repulsion means what? Already there are 9 electrons. Right? Already there are 9. Now you are adding the 10th electron. See, listen to this point very carefully. You are adding the 10th electron. Okay, so there will be lot of repulsion from the already existing 9 electrons. Can you see already existing 9? You are adding that one more, lot of repulsion will come. And size also very small, remember. Rumba Kuttiya, very small size. Lot of repulsion. Okay, so difficult to add this electron. Very difficult. Okay, though you are getting that octet, slightly difficult. But chlorine, that problem will not come because chlorine is bigger in size. So if you see the size of chlorine, right? Okay, slightly bigger. So you can add electron comparatively easier. Comparatively easier compared to fluorine. Okay, so that's why you have this problem. So the order, students, will be chlorine greater than fluorine, right? So chlorine will have higher than fluorine actually, right? Is that clear? So it's a very important point. Ideally speaking, fluorine should have, but because of the repulsion, you know, chlorine will have higher. I hope you're getting this right. Now this problem, you know, continues in the other periods also. Have you copies down? In fact, if you see the oxygen family, oxygen, sulfur, selenium, tellurium. Okay? You will be very surprised. The order what we expect. The expected order is what? Tell me. Oxygen greater than sulfur, greater than selenium, greater than tellurium. Am I right? This is what we expect. We expect that oxygen should have the highest, but shown there's a very drastic change. Sulfur, this is what is expected. The observed one is, I'll write here, the observed order is, okay, the observed order is sulfur comes first, then comes selenium, then comes tellurium, and then comes oxygen. You see the total drastic change, can you see? Sulfur first, selenium, tellurium, oxygen, but end. Why oxygen is having very less? Thanks to the small size. So oxygen is having a very, very small size, extremely small. So difficult to add electrons. Okay, though it will complete the octet, everybody will complete the octet, but oxygen very small size. Please remember this order, very important. Sulfur, selenium, tellurium, and then oxygen. Okay. Can you please note down this? Okay, students. So this is the order you will get, right? So these are some exceptions, like, okay. Fine. So in nitrogen family, if you see nitrogen family, right? Nitrogen, phosphorus, arsenic, antimony. Actually, nitrogen should have more, but then phosphorus has more. So this will be the order of, okay. Clear? Phosphorus has got more. All this is because of the small size of these atoms, nitrogen, oxygen, fluorine, right? With order. Okay. So Shwan, this is one exception of electron affinity. Fine. Now, how do they ask questions in the exam? Okay. Before I come to the questions, actually, oxygen, you see, you add one electron, it will become what? O minus. Fine. Now here, energy will be released. See, when you add the first electron, energy will be released. That means oxygen likes to have the electron. Clear? But students, second electron will be very, very tough. Yes, very tough. One electron, okay, you can add. Second electron, too much repulsion. So already there are 8 electrons in oxygen, remember. Okay, 8. You're adding the ninth one. Though oxygen likes to have, but then, existing electrons will repel. Clear? So one electron you have added, okay, energy will be come out. Energy will release. But second electron, very, very tough to add. So here students, instead of energy released, energy will be absorbed. So here, energy will be absorbed. You have to supply energy. What is the meaning of you have to supply? You should force the electron into O minus. It doesn't readily accept it. Just force it, right? So you have to supply energy. Very important. Okay? So in the first case, energy will be released. Now, let's see which is more. If suppose this energy, we can find out from books actually. Yes, students, 1 minute. Suppose the energy that is released is X. Okay. Now, whenever energy is released, we write a minus sign. We write a minus sign. Okay, that is sign convention. Energy released now minus 4 no. X is the energy released. And suppose here energy absorbed is Y. So we'll put plus. Okay. Now in this case, the absorbed energy is very, very high compared to the released energy. Clear? Energy release means you put a minus sign. So X is far, far greater than Y. I'm sorry. If you write the other way around, the energy that you have to supply, okay, very important point, so listen. The energy that you supply will be very high compared to the energy that is released. Okay, I'll give an example now. Suppose energy released is like 50, but you have to supply 200. So that means you really have to force the electron into oxygen. Not that easy. Okay? You see, you're getting benefit of 50. This much energy comes out, right? Okay. But you have to spend so much. It is like spending 200 rupees. Remember, it's something like this. Spending 200 rupees and only 50 rupees, you're getting it back. Clear? You're spending this much energy, getting back only 50. So your loss of 150, right? So you really have to supply more and more energy. That means you have to push two electrons. So pushing two electrons into oxygen is not that easy. It's very tough. Students getting it? Okay. Then a question will come to your mind that, sir, you are telling that O2 minus is very difficult to form. It's very difficult to get O2 minus, right? You have to supply energy, right? But sir, many compounds, you have got MgO. There are many compounds which contain O2 minus. Na? I'll write some examples now. For example, MgO, Na2O. There are so many compounds which contain oxide ions, minus two, like that. You have so many ions, you can write so much, like lithium oxide, right? So, sir, you are telling that O2 minus is difficult to form. Am I right? But, sir, then how you are getting O2 minus in all these cases? Very surprising, huh? Right? On one hand, I am telling that it is not that easy to get O2 minus. Please understand this concept. It's very difficult to get O2 minus, to push the electrons, right? But then in all these, you are getting O2 minus, O minus 2, right? How? Okay. The reason is the force of attraction, listen here, the force of attraction between magnesium and oxide ion is very, very high. There's a huge force of attraction compared to the energy that you are spending. Okay? There's a huge force of attraction. Is that clear? It's something like the just, I'll explain it. I told 50, I told 200, right? So 150. So you are spending 150 on forming this oxide ion. Am I right? 50 comes out, you are spending 200, right? So 150 is what you are spending on O2 minus. But when you form this magnesium oxide, when magnesium combines with oxygen, right, they are so much attracted, right, that maybe 1000 energy will come out. 1000 joules will come out. This energy released. Now you see there's a huge profit. You see, you're spending only 150. Fine. But you're getting back how much? 1000 rupees you're getting back. So is there a profit? It's a huge profit, right? Clear? Because there is a huge force of attraction between magnesium and oxide. They'll come close together, right? So advantage is there. Okay? So what I want to say is that these oxide ions will not exist independently. But in combination with cation, they'll exist. Or cation irundhuna, anion will exist. Taniya irukadu. Taniya irundha, it is unstable. It's very unstable if it is alone. If somebody is there along with it, right, like magnesium ion, calcium ion, right, then it becomes stable. Then it becomes highly stable, like clear. So 1000 energy is released. Okay? So students, are you getting this logic? Okay? So for the last, for the last 10 minutes, I am explaining you that though it is difficult to form oxide ion, you have to spend a lot of energy, right? But then it is profitable when it combines with some cation. With some cation, it's very good. You get so much benefit. You get 1000 joules energy coming out. Okay. So that's the reason oxide ions will exist along with cations. So I hope you are getting this. Very important point, right? Okay. Fine. And always remember, second time, if you want to add electron, it is always difficult compared to the first time. Okay. And third time will be even more difficult, right? Okay, fine. So I hope you are getting this, students, right? 1 minute. Now, again, students, you will get some questions like this in the exam. Let me give you some questions here. Let me ask you one thing. Let me give you one question. Listen here. Suppose I am asking like this. Okay. I want to convert C minus to C2 minus. I need to add one electron, right? Is that clear? C minus to C2 minus, N minus to N2 minus. Question will be, where is the electron affinity high? Okay. Is the electron affinity of C minus higher or is the electron affinity of N minus higher? That's what they will ask you. Who has got more affinity for electron? Who likes electron more? Let's see the answer now. Okay. See, like let me repeat, both are difficult. I told second electron, it's difficult, right? Second electron. But the question is that which is more difficult? Both are difficult. One electron and again one more electron, both are difficult. But let's see which is more difficult. Okay, or which is slightly easier. Okay. Now, student, how do you do this? You write the configuration of carbon. What is the configuration of carbon? 6. Correct? Is that clear? Okay. Now you are adding, listen here, you are adding one more electron here. So when you add one more electron, just see, very interesting. This is the configuration of carbon. Okay. And this will be for C minus. C minus means you are adding one electron. You see from 2p2 it has become what? 2p3. Am I right? Now, students, you know that half-filled orbital is more stable. C minus, 2p3, 2p2, right? Half-filled is more stable. Is it half-filled? Tell me. P can hold 6 electrons, na? So this will be half-filled. Correct? So now it will be difficult to add electron to C minus. It will be difficult. Why? Because you are getting a stable configuration. Can you see? Difficult to add electron. Because you are disturbing the stability, right? Let us check for N minus now. For N minus. What is N? 1s2, 2s2, 2p3, right? What is N minus? 1s2, 2s2, 2p4. Yes or no? And what is N2 minus? 1s2, 2s2, 2p5. Okay. Now if you want to convert N minus to N2 minus to N, it is difficult. See, again I repeat, it is difficult, but you are not disturbing any half fill, nothing like that. See, 2p4, correct? No disturbance of half filled. Clear? But here you are disturbing a half fill configuration, disturbing a stable one. Okay? So the answer is C minus, okay, will have less electron affinity compared to N minus. This is the answer, stone, right? C minus will have less electron affinity. It doesn't like electron much because of its stability. Okay? So it is easier to add electron in N minus compared to C minus. C minus will have less affinity. Okay. So student, all these questions, you can do if you are able to write the electronic configuration, right? Okay. Just go by half fill, completely fill, right? Okay. So I hope you're getting it. Note down this, very important. Yes, student, have you noted down this? So it's all about electron affinity, right? Now, one small question, I want to ask you. Metals will like to lose electron. Okay. Non-metals will like to accept electron. Clear? So therefore, can I say all non-metals will have very high electron affinity? They like to accept it, right? Okay. Non-metals have very high electron affinity. Metals, they lose. Right? Okay. Okay then students, I think we'll stop here. So that's all about electron affinity. Okay. So we'll continue with this next time. Okay then, bye then students, bye. Take care. Bye.